Good afternoon. Welcome to the CERIAS security seminar at Purdue University. Since today is the first lecture of this semester, I'll explain some basic rules. So for those of you who are taking this for credit, you need to sign up on a sign-up sheet each time, check your name. And if you miss more than 2 lectures, you have to make up for the ones over 2. You do that by watching the video online afterwards, and then send a 1-page description of the talk to me to prove that you have watched it. And because the CERIAS computers are down today, so we do not have the actual sign-up sheet ready. So we just have we'll just hand out this piece of paper so that you can write down your name and sign. So today it's my great pleasure to introduce Professor Cristina Nita-Rotaru. Professor Nita-Rotaru joined the Purdue Computer Science Department the same year as I did in 2003. Actually, I think we've been next-door neighbors.
Yes, from the beginning.
From the beginning.
Yes, yeah. Although we moved in a different building, yeah. But we still.
Yeah. So Professor Nita-Rotaru has been very active in networking and distributed system research, and he has had several very wonderful students in the past. And today, he will talk about secure network coding for wireless mesh networks.
Thank you very much, Ningui. And it's great to be here. I was actually making the comment that I will never work in television. I hate these lights. So you have no idea how bright they are, and they just come to your eyes. I'm also very glad to see a few familiar faces here. I've seen some of you guys in the past, so it's nice to see you here. What I want to do today is to tell you a little bit about some of the work that I have been doing with a former student of mine. He just recently graduated, and another student that was a postdoc here, and he's now a faculty member at NGIT. And before getting into this talk, I wanted to ask how many of you took networking? Okay, so when we look at networking, how do you, what's the first thing that you learn in terms of how packets are sent from one party to another? So what will a router do? The most basic action. Hi.
Examine the destination.
And do that what?
Look up tables to figure out what to do with it.
So, but the most basic action is actually just to forward the packet, whatever packet was received. The reason that I'm saying this is because network coding questions and proposes a different way of building networks, starting with this very basic action. So you are all used from networking classes to look about and think about protocols as the traditional routing where any participant in a network protocol will forward the packet in the form that it was received. Network coding proposes a very different way of building networks. So what it proposes is, instead of just forwarding the received packet, a router or an entity that is involved in the routing process will wait for a certain number of packets, and then what it will forward is a linear combination of those packets. Okay, so you receive certain of them, you send only one out. It turns out that this very simple idea actually allows you to build systems with benefits in terms of performance that we were not able to do before. So we can get higher throughput, higher reliability, robustness, energy efficiency, and we can leverage this type of mechanism for many applications. We can leverage them for wireless, for peer-to-peer systems. There are proposals also of how to do this for delay-tolerant networks, vehicular networks. So I just wanted, this is not a lecture about network coding, but I just wanted to show you 2 examples of why people were very excited about them when they first were proposed. So for example, you can really get better throughput. So if you look in the 2 diagrams that we have here on the page, on the left, no matter what you do, if you want to do multicast, your throughput is always going to be 1 because you're limited. If you look, this is called the butterfly network. The link that is in between, if you want to send 2 packets, you can never send more than 1 packet on that link. That link is your bottleneck. However, with network coding, which, as I said, the main idea is that you or the routers are allowed to send combinations, linear combinations of received packets, you can actually get a higher throughput. Why? Because on the bottleneck, I can set a XORed message, like I can share A XORed with B, so I can still send one message that contains the information about both messages A and B, and at the same time, the two recipients, they can actually recover both packets A and B. Okay, so there are some advantages. I want to show you another example, the one with delay, because this is also something that is interesting. Just think about, you want to do multicast and you want the source to multicast 2 packets to 3 receivers. If you look at the example in the left, no matter what you do, it's always going to take you 3 hops to send the packet. And actually with network coding, we can do that in 2 hops. If one of the packets that it's sent, it's actually a coded packet. It's going to be the XORed of the 2 packets that I wanted to send A and B. So these are just some examples, but in order for network coding to work, there are actually some assumptions. So the assumptions there are is that, let's say that somehow, first of all, there is this, or what it can be leveraged and it can be useful if broadcast comes for free, right? Which is very, for example, is very natural in wireless networks. I send the packet, everybody that is around can hear it. The other thing that it's very useful if you can have this type, it's called opportunistic listening, which basically means you are in the proximity to receive some packets. And those packets may not necessarily be for you, but the assumption is, think about the example with A XORed with B and B where you want A. You can always get A if you have the XORed of A and B and B. And the B you maybe received it just because you were around. It just happened that that packet was broadcast and you were in its proximity. So because of that, you can get all these benefits that I was mentioning before. Now going to how people thought about to apply network coding in the context of wireless networks, which they're really a very natural environment to try to build network systems using network coding. People thought about coding in 2 ways. You can code within the same flow or session, which means you have one source that has to send packets to multiple destinations. So you can code packets across this flow. Or you can cross packets, we can code packets across multiple flows if you have multiple destinations in the system. So as a classification based on how coding is done, we have systems that they're called intra-flow network coding systems and others that are called interflow network coding systems. So both of them have certain aspects that, as we will see, make them less robust when we start to think as an adversary. So I wanted to show you an example of how do you take that simple idea of just, I'm not going to forward the packet, I'm going to forward the linear combination and actually build a system. So for example, when we look at the intra-flow network coding system, the way systems like that work is that the packets that have to be sent by the source are divided in what they're called generations. So you can just think, I'm going to divide these packets in groups. One such group is called generation. And what happens is that the source is going to move from one generation to another. So when it wants to send the generation, the goal is for this set of packets to be received by the receivers. It's going to be a set of them. In this picture, we have only one of them. So how it works, the source is going to create coded packets based on these packets from the generation. Many systems, what they do a random linear combination of this. You just randomly generate coefficients and you create a linear combination of these plain packets. You obtain a coded packet. And then forwarder nodes, what they do, they will buffer the overhead coded packets. They may decide to create new coded packets. So again, we're going to have other linear combinations. And the reason why all this works is because if the receiver receives as many packets as the generation, how big the generation is, recovering the plain packets really comes down to solving a system with n unknowns, and we have n equations, we can solve it, the receivers can recover the packets. Okay? And once that happens, the receiver will tell the source, got the packets, move on to the next generation. It's not so complicated. Now in Interflow, it's slightly more complicated in the fact that because we have to mix now, or the system have now to mix packets across multiple sources, and then it's not always easy to decide when can you code. The reason is because not everybody has to receive all the packets as in the previous case. So there are some conditions that have to be met. One of them is this decodability condition. So in other words, in order to be able to decode, you will need to have the other packets that were part of the combination in order to create that. So this brings me to why I care about all this. I care about, not that I don't care about network coding, I think that they're very important, but I care about security, and if I'm an adversary, I always think about, okay, this is a new system. It looks like it's so good because it optimizes and it has all this great performance. How is it going to behave if some of the nodes, or if the system is placed in an adversarial environment, or maybe even some of the nodes don't behave correctly? And the thing is that if you think about network coding, in some sense, just because of the fact that the routers now, they have to create new content based on previous content, they really do change the trust model, right? Because the routers now actively create new content as opposed to just forwarding what they received before. And that changes a lot the rules of the game. So what I want to do in the next few minutes, I want to give you some idea of what type of vulnerabilities can happen in systems like that. And to keep the discussion focused, I'm going to then pick one particular attack that it's both new and very damaging. And I'm going to keep the discussion in the context of one class of network coding systems, which are the less complex one, the one where the coding happens within a flow. And I'm going to show you, some limitations of what some other people did, what worked, what didn't work, and I'm going to show you our solution and some experiments and what happened there. And just to keep things clear, when I talk about network coding, I mean network coding at the routing level. So the attacker is not messing up with the MAC. I assume that I can trust the MAC, and that the attacker will do things at the routing level, like eavesdropping, injection, modification, and all kind of other wireless specific attacks. But first, let's get even more in details. So I give you some idea of how you would do intra-flow with for example, with the generation. The reality is that in wireless, you cannot have all nodes starting now coding and sending at the same time because you have collisions. So you can end up with having higher error rates. So there are a little bit more complex things that you need to do. You need to be a little bit more careful if you want to design a system that works. So when you look at the intra-flow network coding, for example, components that need to be addressed and they are part of design of such system. One, and the most and doesn't look like from in the beginning that you need it, but it's actually very important, is to select who nodes are going to code and at what rate. Rate is important. You cannot just start sending, because you're going to have collision. Then obviously we have the coding and decoding part, which is really the core of the system. And then we need this acknowledgement that will basically tell the source that now the source can move to the next generation. And also the Interflow network coding has some components. We have to discover when can we code. Then we need to do the coding itself. And systems like that, because they're very optimized, actually they integrate with the routing itself. I'm not going to get into that many details there. So let's look a little bit at this intra-flow network coding, give you some idea. Now, if I'm talking about selecting the nodes that they're going to forward and what rate they're going to forward, the way these systems work, they assume global knowledge. So the source needs to know what are the links and the quality of links in the system. And basically, based on that, it will decide at what rate has each node has to forward, and it will tell each of them what they need to do. And one big component here, for example, is how the nodes exchange information about what is their link quality metric. So, for example, things that can go wrong here is when the nodes start lying about their link metric. And if that doesn't happen correctly, in other words, if the source has incorrect information about the quality of links, what the source will decide obviously will result in something that is incorrect with respect to the node selection and rate assignment. So you're going to have performance degradations. So how can a node, for example, lie about the link metric? And these are very basic problems in general in what is known as Byzantine Resilience, which is all this area of how we design systems where people, processes, nodes can lie. You cannot trust what they're saying. So for example, in the first case, so the nodes, what they do, they measure what is the link quality and with respect to the previous nodes. And what they have to do is tell the other node, for example, node B that I have here with red, he's supposed to tell R, my link quality to the source S, which is the green, it's 0.27. Why? Because the link quality from B to A is 0.3, from A to S is 0.9. Now, if he's not correct, he's going to lie and he's going to say, oh, my link quality is terrible. It's not terrible, it's very good. So he can say 0.9. And what that will result is the fact that that guy would always be preferred. So he attracts traffic. Now, I should mention that in this case, it's actually difficult to prevent completely this attack from happening. The reason is because there is no way I can verify really what's the correct there unless I have some other trusted source of information. Now, this node, the same node B, what actually can do, he can also try to lie about what other nodes said. So when he is trying to lie about what A said that his quality, link quality is with respect to S, or that type of thing I can prevent. Why? For example, just think about maybe digital signatures or encryption. Of course, those are not be scalable, but I'm giving some example of why you can prevent those type of attacks, because you can prevent malicious nodes from modifying information that comes from other nodes. Okay, so data packet forwarding, that's easy to figure out what the attack is. Basically, there is always, if you have a malicious node, he can just drop packets. So this will really focus on the data forwarding component. So what can make it here problematic is an attack is very simple, actually. And also you can see what the effect is going to be. Packets are not going to make it, so the routing doesn't work properly. What is interesting in this aspect is the fact that whatever we know how to deal with this type of attacks from traditional routing, you cannot just apply it here. The reason is because if you think, for example, the most basic technique that we know, which is monitoring, here, whatever it's forwarded is not equal with what was received. So then what am I monitoring? Because they're not going to match. So it's not that trivial to apply. The acknowledgement delivery component is the one that we know the most how to defend against. So just give you some example of what can happen. Remember that this acknowledgement is sent by the receiver or the destination when it could receive all the packets from a generation. However, the systems that I described, none of them use any type of any protection. You know, it's I teach 355 today, and not today, this semester, and I taught it yesterday. I'm going to teach it tomorrow. And students always assume that confidentiality is the most important. For network protocols, actually, authentication is much more important. You know, authentication and integrity. Who sent the packet? Is that the right packet? So, for example, just because systems like that have no type of protection, an attacker, which is the red guy over here, he can just randomly send some acknowledgement. Or he can just drop the right acknowledgement. So what can happen in this case, which, by the way, these are attacks this is an attack that's not always easy to detect, because it's not the type of behavior that it's easily detectable. In the first case, the source will just start sending a new generation because it will assume that the correct nodes receive the packets. In the second case, we'll just keep sending the same generation. Even if the poor receiver said, I received the generation that you sent before, please give me the next chunk. You know, I want to watch the movie. Give me the next chunk. And the source will not be aware of that and will keep sending the same information. So in this case, there are things that you can do that we know how to do it to deal with Byzantine attackers. The obvious one, you can always flood, right? It's one packet. You don't want to do that in general just because obviously it's going to have a higher overhead. But at least I would say that here we have some idea. Now what I want to focus on is the new part in the design of such systems, which is the coding and decoding. And I have to put some math into here, into the presentation, right? Just to show you that actually coding it's very formally specified, and we can also specify very formally what can go wrong here. So really sending a coding packet, what really means you can actually express it in the form of a multiplication in a particular group where what the coding packet really represents is going to represent a vector of coefficients, and the coded packet itself is just the combination, the linear combination using the packets from the generation G and the random linear coefficients C1, C2, Cn that were created. So what is really sent over the network is going to be sent C, which is the vector of the coefficients, and E. That was the coded packet. Now, what can go wrong in this context, which may not seem very obvious in the beginning, is that when we're talking about coding, the network coding, coded packets themselves can be used later on by other nodes to further code, to even further improve the performance of the system. So we are used to think about injection as something that is easily preventable. However, in the context of packet coding, such injected packets, which people call polluted coded packets, can create a lot of damage. So a polluted coded packet is basically a packet that will not verify the fact that E, which is the linear combination, was created using the coefficients that are represented in the code, in the packet that is sent. It can be just garbage there. Okay, but if you formally want to express it out, how do you express it? Basically, it's not going to verify this condition. Actually, this is a generic attack against any type of network coding, not only wireless, but it's particularly detrimental in wireless, and I'll explain immediately why. So if you really want to see what happens when such an attack is created, just think about the initial red packet as a packet that is not correct. That packet is going to be further used in coding other packets, so you can end up with a situation, this is a little bit of an extreme case, but you can end up with a situation in which basically the receiver cannot decode anything. So the throughput can be 0. In reality, it's not exactly 0, how I will show you in experiments. In reality, you end up with almost 0. Why is not exactly 0? Because not all packets code. That that rate assignment and forwarding node selection and rate assignment basically selects a set of nodes that will forward. So that's why you may end up having some packets that they're good, and so that's why you don't have exactly 0. Now, in the context of wireless, the reason that this is very problematic is because wireless is a very resource-constrained environment. So you're really using the biggest resource in wireless is bandwidth. So you're wasting all this bandwidth sending incorrect packets. So this is the problem, and it looks like a very simple problem. And when first time people look at it, it's like, I don't understand why this attack is an issue, because it looks like in authentication, I can authenticate all packets. Why is that a problem? So the reality is that it's not as, I don't want to say easy, but it's not really an old problem as people think, because one of the issues that happens is that if you look at the forwarder, so how can you prevent this attack? You really want any intermediate nodes, and I emphasize that you want the intermediate nodes. You don't want this detection to happen at the receiver, because if it happens at the receiver, you already wasted a lot of bandwidth, so the performance of your system is going to be really terrible. You're going to be able to detect this at intermediate nodes. So what you want an intermediate node to be able, when it looks at the packet that it's coded, to be able to say, oh, this comes from the source. And to keep in mind that that coded packet actually can be a coding of other coded packets. So in other words, if you really want to be able even to apply things like, think about digital signatures, what I would say, oh, I will have the source signing the packets. You need to have the source to be able, for example, the brute force type of defense will be the source has to sign any possible linear combination. That's not scalable. right? If you don't want to do that, then what you want, if you want to apply cryptography, which is the first thing that will come to your mind, you need an authentication mechanism that has homomorphic properties, right? You need it to transfer, to keep the same property across the coding, which is basically a linear transformation. And that can be a hash, it can be a digital signature. So that's kind of what people thought that it will be a good idea, and they actually went and designed schemes like that. There are actually lots of digital signatures for network coding designed for pollutions that have homomorphic properties, and they do work. And I will show you what type of performance do you get when you start using them in systems. So they're very expensive. There are so many exponentiations in there that your performance goes down to 10%, 20%. I'll show you experiments immediately. Now, there are some other ways which you can do. So some other direction is to look from because network coding came from the information theory community. So another way to look at it is, okay, if I assume that some of the nodes are going to try to pollute, can I add the redundancy in the coding itself, such that even if some packets are incorrect, polluted, I can still recover the packets. So that is a method that actually works pretty well. The only thing to keep in mind that when you're doing that, you're actually reducing how much you can improve using network coding over not using network coding, right? Because you're doubling a lot of the information that that you're adding when you're coding, and that's where your resilience to attacker is going to come. Also, those particular type of methods work very well, for example, for peer-to-peer systems, but not so much in wireless, because it really constrains, or where they're limited is how much bandwidth has an attacker available. And the reality is that if the attacker is near the source, it controls all the bandwidth. So that is possible, particularly in a mobile network. And then people also look at network error correction, but those really, they're not designed for adversarial environments. So I promise that I'm going to show you some graphs. This is the first graph that Jink came, when he wanted to work on this, and I say, well, why cryptography is not working? And he came back to me with this graph. This is actually an implementation. It's a simulation, but it's using real data link quality from the RoofNet testbed at MIT. And what you see here with the black, you see the performance of a well-known system that is doing intra-flow network coding, and this is more. And what you see with red is what happens when you are using one of these homomorphic digital signatures to protect against network coding. And what I insist, and is written in green here, is this happens when you have no attacker in the system. Okay, so if this would have been not working, I would have asked you, so what does it mean when we see the red line so close to the y-axis? Is that good? Is that bad? Anybody here? It is very bad, right? It is very bad. That basically means that a high percentage of the nodes in the network get a throughput of almost 0. So this is very bad. Why do they get that bad performance? Because the computational cost of these digital signatures, the homomorphic digital signature, is very, very high. This is one example of a scheme. Actually, we evaluated many of them. So it's not a problem with that particular scheme. It's just a technique, is just the limitation that cryptography brings to such systems. And we have many schemes that we looked at. There is one scheme that does much better than others. It's called HomoMAC. It's actually not a digital signature, but a MAC. And it's the one with the black here. So you can see that it's in a class by itself, because it's really kind of in the half. So it's doing much better than all these guys over here. What it's not seen here in this particular graph is that with HomoMAC, it limits the performance. It relates to how many attackers you can tolerate. So unlike a digital signature where you generated the signature, and for most of them it doesn't matter how many attackers you have, in this particular case it does matter. But I don't want to get into more details. It does better than the others. So what we wanted to do we wanted to see, is there a way we can move that bar? We want what ideally you want for a system. If you ask anybody that uses any type of system, they don't want to feel the security, the cost of security, and particularly when there is no attacker in the system. So what we're trying to see is, can we have some type of solution where the performance of the system is very close to the unsecure system when there are no attackers, and maybe we pay some penalty when there are attackers, but not to the level that the system becomes unusable. So we say, okay, if we cannot use crypto because crypto has this problem, is there any other way we can do? So one thing that we can do, and that's what we came up with the idea. Well, first, if we don't want to use crypto and we want to use what is very cheap, is there these checksums that involve just linear transformations. So those are basically multiplications as opposed of exponentiations, which all these homomorphic schemes require. We say, okay, we're going to do something like that. So we're going to create we're going to have the source creating a checksum that is disseminated periodically. We're going to have also the timestamp when it was created. We know that this checksum is sent authenticated, so nobody can then inject it. And we can use that to check if a packet is coded correctly or not. But there are two caveats here. First of all, this is not a hash. So because it's not a cryptographic hash, it is not pre-image resistance or collision resistance. I don't know how many of them. Actually, there are some people here that do crypto, so you should know what pre-image resistance is and collision resistance is, right? So it doesn't have those properties. So then the whole trick is, okay, where do you get your security? What prevents an attacker from forging packets? So the whole trick in our entire scheme, it's actually in the way the check is enforced. When I'm going to check, so what the nodes are going to do are going to check packets against these checksums that are received periodically from the source. The whole trick is these checksums have to be created by the source at a time that is after the packet was received by the node. Okay? And I will explain why that is the key. So let's look at a very simple example. So I have the source, I have an attacker, I have time, and I have the correct node. Because this is not a cryptographic hash, that means that when the attacker node A sees the checksum CS1, because this is not a cryptographic hash, he can actually generate a packet P that will match the checksum. No? If this would have been cryptographic, that would not have been possible. But in this case, it's possible. So then attacker A thinks he's smart. He's going to assert this packet P to B with the goal to pass the verification scheme. And the whole trick is that this packet P that was received by the correct node B will never be verified against the checksum CS1. It's going to be verified against another checksum that was created at a time that has to be bigger or later after the packet P was received by B. So in this case, it has to be bigger than T3. So CS1 will never be considered as a point for verification. So if you really want to see what is really the key to make this work, is this particular slide. Now, to actually have this working in a system, we'll see that we have to get into more details, but that's really the main idea. So in other words, again, the fact that the attacker can see these checksums in the clear doesn't reveal any information. What is important is that an attacker cannot inject checksums, and that's why those checksums have to be authenticated and they carry timestamps. So attacker cannot inject, cannot modify them. So let's look a little bit at the details. I'm going to show you two systems. First, I'm going to explain the main idea with a system that is called DART. And then I'm going to show you how you can improve over that to optimize the system even more. So we can express, I'm not going to get into all the details, but actually you can express mathematically what that checksum generation and verification means. This checksum, it's random, so the source will do this periodically. Now, there are some elements that we can use in our design to control the size of the checksum. We don't want the checksums to be very large. We want the checksum to be very small because that's overhead. There are some advantages of our scheme. For example, there are no false positives, right? So and also that the verification, again, because the checksum it's a linear combination of the packets that were sent. the verification is really a multiplication, a matrix multiplication. So it's actually very fast to verify something like that. We can also do what all the systems actually do when they propose verification for packets. And I bypassed this first because I wanted first to give you the idea. But the reality is that systems, including our solution, you never verify one single packet. You actually verify a batch. Why? Because that, again, gives you better performance. So as the other schemes, we can also do batch verification. And in case, you know, we can say that they're all valid. If they're not that valid, we can figure out which packet was the one that was polluted. Again, very fast, so that's not an issue. Now, in terms of how would you take this and integrate it, if you remember the first slide that I showed, oh, not the first, but maybe 4 or 5, when I was showing you how intra-flow network coding systems work, the changes that will happen now is that when packets are received, coded packets, they cannot be forwarded immediately. So if you look at node D, he's going to have 2 queues now. Packets that are verified, packets that are not verified. So the ones he can verify a packet only when he received checksums that have timestamps after the times when those packets were received. Then he can put them in the verified. If there are enough of them, he can code. He can send them later to the receiver. When the receiver has enough of them, can decode. Okay. Now, with this scheme, we can actually analyze, we can tell exactly what is going to be the computation overhead, the communication overhead. We can control how big the communication overhead is, and I have here some examples. What will be, there are certain parameters that control the layout of the network coding in terms of how big the coefficients are going to be, in what group are you going to do these operations. And I had here some example, in a typical network coding system, for example, if I use the random seed to be 4 bytes, the timestamp 4 bytes, and we have this control parameter that controls how big the checksum is B, you can come up with it to be 64 bytes. So it's not that big. I also wanted to show you that we can also analyze what is the probability that a polluted packet will pass. Why would a polluted packet can pass such a verification scheme? Can anybody think about? Collisions or just random guess, right? The attacker is just lucky. So basically that's what it happens. So if he's very lucky, what we can actually show that there is obviously some probability that a packet can pass, and that probability it's actually very small. We can also show that what is the probability if you're doing the batch verification based on how big is the window for the batch, and also what we can also show is that if you want to repeat the procedure, what will happen. And I have here an example, basically that if I look at the typical network coding system and with the B parameter of just 2 that I was mentioning, basically 1 in 65 5036 polluted packets can pass over the first hop. So that's actually a very small probability. Even if it passes, then with this 1/4 billion, he's going to be caught at the second hop. So that's even better. But, and this is where it gets interesting, obviously you never get so, you know, I just focus and I keep showing you, right, what is the cost of cryptography and how we're not going to pay that cost. But nothing comes for free. So there is something that you do pay with this scheme that I described. Anybody paid attention and think?
Like latency will go up.
Yes, very good. So that's actually what happens. Now, again, I didn't give you all the details. There are things that you can improve using a technique that is called pipelining. But the reality is you cannot, or with the scheme that I just described, a node will not forward the packet immediately. Okay? That's not what we want. Because I told you before, what we would like, if there is no attack, we would really like not to feel at all the cost of the scheme. So that delays, as you guys observed, it delays the packets for verification. And what we actually would like is to delay only the polluted packets, right? The correct packets, we want to send them immediately. Obviously, we don't know which ones are polluted and which ones are not before we verify them, okay? So we have to make a decision of how are we going to start this. So what we came up with is some type of adaptive scheme. And we're going to start under the assumption that there are no attackers, which means we're going to be positive, optimistic. So what we want to do is to forward packets without delay, but we cannot allow we will need to verify the packets eventually. So the fact that a packet is forwarding that without delay doesn't mean that that packet will not be verified. It's just like I will not verify it at that moment. So I'm taking a risk. The risk that I'm taking is that that packet maybe was polluted. If the packet was not polluted, I'm good. I got the performance and all that. If the packet is polluted, I'm taking a risk. So that's why I don't want to always forward packets without verifying them. So I want to constrain how many hops a packet can be forwarded immediately without delay. And the way I will do that is by using some additional information on a packet, which is going to be a hop count. So again, ideally what I want to restrict for how long a polluted packet can travel. And I want, if there was no attacker, things are always going to work smoothly. So I'm going to show you the details of the scheme. So I'm going to add on the packets a hop count, which basically will say how many hops as the packet traveled since the last verification. When the packet is verified, that hop count will become 0. And for our purposes, actually, we don't protect this hop count. And we can brainstorm about why we don't protect it, what can go wrong. So ideally, what an attacker wants to do, obviously, if the attacker puts the hop count to be very small, not to his interest, right? So the only thing that he can do is he wants to make it very large. And because if he makes it very large, then we're not going to verify too long. Now, at the same time, in order for the attacker to really be able to travel for a certain number of hops, because it's going to be verified all the time, it really has to have kind of a chain, which is a little bit more difficult to achieve. So in our case, we made the decision that it's not worth it to protect it. So this is how it will work, exactly as in the things before. Now, nodes are going to be in two modes. They either forward immediately or they delay for verification. So we're going to have a forwarder time, and we're going to have this additional h hop count that will be on a packet. And this is what a forwarder node will do: waits for the packets, and he will have to decide when he needs to verify the packet immediately. So hold it, not verify immediately, hold it for verification without forwarding immediately, and when he can forward it immediately. And the other thing that we also want to do, which is something that I don't think that I mentioned, we also want to penalize the nodes that when we see that a polluted packet was detected, then we want to restrict, we want to verify for a longer amount of time that packet, because we want to be a little bit more cautious there. If that's not the case, we decrease that because we want to, in case we made a mistake, to drop the verification. So that's how we constrain for how long are we going to verify, for how many hops are we going to verify the packets. So this is just a simple example that will show you, for example, what can happen if there was detected that there was a polluted packet. So initially all the packets are in the forwarder modes. A is the adversary, A sent a bad packet, and everybody immediately will switch to the forwarding mode, to the verifying mode, because detected a polluted packet. What we want here is the following. What we want is that the nodes that they're closer to the attacker to stay longer in the verification mode as opposed to the ones that they're further. Why is that? Because the assumption is that if I'm further from the attack, most likely somebody before me with a less number of hops detected, so there is no point for me to pay the penalty. And that's why we have that adjustment with the counter that I was saying, that we adjust of increasing for how long nodes are going to be in a state or not. Now, another thing that I wanted to show you is that there are two parameters that we actually use in this system. This is where the system design comes into picture. So what we want is good security, but we don't want a lot of delay. So when we are looking at the analysis, it comes down to actually two parameters. One is how many hops I allow to delay, and another one, which is this alpha, is how I decide when to stop verifying. And it comes down that if you are looking at, for example, how I define security in terms of how many packets and how long I allow this pollution to happen versus performance, which will be unnecessarily delay, it comes down to really manipulating these two numbers, alpha and rho. I can express everything based on these two parameters. And that really basically allows you to decide, do you want to be more aggressive in terms of security and you're going to pay a slightly higher delay, or you want to be higher on performance and with the assumption that you know that you're going to have some polluted packets. So going further, I wanted to show you also the experiments because we implemented everything. So this is the picture of the RoofNet testbed at MIT. The way we perform these things, we have, so what we can get from this particular project are the link qualities of an existing testbed. So the link qualities, we take them, we use them in a simulator, which is the GlomoSim simulator, which gives us a network coding system running in a simulator, but with link qualities that come from a real testbed. We use the implementation of More. For the dissemination of the checksums is the only place where we need digital signatures because we do need the source to sign the checksums. And this is the one that shows you, for example, just the attacks. If you wanted to see when only, so this pollution intensity for us was like, how many packets are you going to inject in the entire generation? And with this picture, the way to read it is that it's sufficient to inject very few packets to actually get the throughput of the system to be 0. So the attack is very, very bad. It's very effective. Now, it's not 0, as I was telling you before, because not all nodes forward. So this, what you see here is really what happens in the context of the RoofNet topology, right? How that testbed actually looks and how the link quality are. If you apply network coding for that system with the system more, that's kind of how effective the attack looks like. So not very good. Now, we can also show you how our system works. And I put here, I should mention that the RoofNet has 33 nodes. So when I say 5 attacks or 10 attackers may look like it's not a big number, but 10 is almost 30% of the entire network. And you can see how the two systems, Dart and eDart, do with respect to an oracle. So what we call ideal is the system that will know a priori which packets are polluted or not, and will know knows the truth, as opposed to our system that has to do the verification and the adaptation. So as you can see, they're actually very effective at detecting the polluted, the attackers. The difference is that when you're starting looking at latency, you can see that, for example, Dart has some degradation. eDart is the one that is optimized with respect to throughput, again, because it's using that delay, so delay also affects throughput. And with respect to latency, obviously, eDart, it's much better because eDart is the one that does not have delay. And by the way, here is benign networks. So in this case, there is no attacker. I just want to see what the system will do if there are no attackers. So before we have the attackers, I'll show you the performance for attackers. Here, you can compare this picture with the one that I showed you in the beginning, when even when there were no attackers with the heavy cryptographic mechanisms, basically your system had almost no performance. So this is something that, that we liked. We also look at overhead, and our experiments basically show that the overhead is very small. If you look at the overall system, it's about 2% of the throughput. So that's for wireless, that is very good. We want the overhead to be very, very small. So to summarize, network coding is a new way of building network protocols. It has been proposed, I would say, for maybe 10 years or something like that. So it's not, as a paradigm, it's not a new paradigm. What is new is that actually there are advancements that make them practical in terms of systems. So there are several systems out there today that that use network coding for different applications, wireless, peer-to-peer, vehicular networks. But people didn't consider, and I think that that's kind of a history with system design. People don't always think about security when they're thinking about how to design new systems and optimizing. So what we did, we looked at how do this system perform when we place them in adversarial environments and things don't go according to how it was planned. And I showed you one particular attack that is very detrimental to network coding, which is pollutions, and show you what was our solution there. And I can tell you that things don't stop there, because this is just like you know, the tip of the iceberg. So there's several of other problems. Ideally, it will be good if you can identify the attacker, because the reality is, and when you do just the detection without identifying the attacker keeps bothering you. So that is additional overhead that you're paying in the system. And there are also other type of attacks, right? I just show you pollution, but in the beginning I give you some idea of other things that an attacker can do. Things get even more complex when you look at interflow system, because, for example, in that case, you cannot do things like what I described before, because the sources don't trust each other. They can actually, why? Anybody can become a source, so can attack another flow, so they can be adversarial to each other. And so then then when you're looking at, again, at monitoring, it's not easy to necessarily apply. So I keep saying monitoring. Why? Because, for example, if you really look at a very simple problem, even like will a node forward or not a packet? Traditionally in routing, what you can do when you apply monitoring, nodes will look like compute the hash of packets that their neighbors received, and compute the hash of the packets that the neighbors forward, and see, do they match? Do they forward what they receive? Is the packet the same? I cannot do the same thing when I do network coding. The input and outputs are not identical. They don't happen at the same rates. So it's not so trivial to just take something and apply it here and it will magically work. And so there are lots of other things that we can do here. Had a few graphs that show you what happened if I look at other attacks. If I look, for example, at just dropping the ACK, that creates you as much damage as just doing very complicated things. So that's what really this shows you, right? Drop all will drop everything. Drop data drops data. Drop ACK, just the ACK for the generation. That is sufficient to get the same type of damage. And it's much more difficult to detect that a packet, one single packet was dropped, as opposed to, because it's a smaller change in behavior than other things. So we actually did more experiments looking, you know, what if you have a single attacker, what happens there. There are lots of other issues. This is just wireless, but there are lots of other issues that we can also look in the context of peer-to-peer. By the way, many systems also look at network coding for distributed storage. That's another area where they're very good. So as I said, this is the tip of the iceberg, and actually have a 4-year project working on this, and you know, we hope to be able to come up with systems that really leverage both the performance of network coding and they're not vulnerable to attacks. Thank you very much.